Hello guys, how are you doing? Just give me 1 second. I need to verify one thing. 1 second, please. Okay, guys, so let's start the class. So let me show you my screen, and then we continue. Okay, so someone can tell me where we have a stop last class, please. Where we have a stop. Someone? We have done FX, right? We have done foreign exchange. We have done, I don't know, we have introduced inflation in the equation or not? Yeah. Okay, so let's do, so basically, I just need to be sure that we have done this. So we said that if this is P in euros, I multiply this by the exchange rate times 0. So now this is in dollars, correct? We have said also that E1 exchange rate at time 1 is simply the exchange rate at time 0, 1 plus the devaluation rate, correct? So if I have my euros and I multiply this by the interest in euros, so this was in euros, if I multiply this one times E1, I have this amount in dollars, correct? Then we said, okay, replace E0 here, so this P euros multiplied by E0, 1 by devaluation rate, 1 plus P euros. Then we said that if I want to find the interest rate in dollars, it's simply this minus this over this. And then we arrive to an equation that look like this. Okay, you simplify and then you obtain and this was your one of the main equations. As I mentioned to you guys, this was a nominal interest rate. If we want a real interest rate, the only thing that we need to do is we simply divide this by 1 plus pi. And then the formula gets modified, of course. So I interest in dollars real was going to be equal to P euro E0 1 plus depreciation 1 plus interest in euros. This one divided by 1 plus pi minus P euros E0 over P euros E0. If you simplify, you arrive to a condition like this one. It's going to be 1 plus over 1 plus pi minus 1. Agree? This was the equation. Okay, so let's do one example. Okay. So let's do one example. Imagine, guys, that you want to invest in USA, okay? So assume, guys, that internal rate of return, so the profitability of the business in USA is going to produce you 7%. Okay? Assume that you get a loan in Europe. in euros, okay? So let's assume that the interest rate in euros equals 3%. Let's assume, guys, that the expected devaluation rate in USA is 1%, and the inflation equals 0.5%. Okay? So given this information, guys, you invest in USA or not? Okay, 3 minutes to do this. Ready? You do it or not? Do the investment? Yep.
Yeah.
Okay, so let's take a look first to what should be the interest rate. As soon as I have inflation, guys, I need to talk in terms of real terms, right? Okay, so let's do first take a look to the what is the interest in dollars, real. So I apply my formula, it's going to be 1.01, that multiplies 1.03, and is divided by 1.005 minus 1. So what do you get here?
3.51%.
3.51%. Okay, so this is real. Can I compare this real with this one here? No. So remember, guys, that if no one tells you anything, the default is nominal or current. That is the same name. Got it? So we need to transform this one here first in internal rate of return real. So what is my internal rate of return real? Do you remember this formula? So let me remember. Yes, so remember, I was saying, the interest rate real, you always need to recover your expense, inflation, and then you need to have a real interest rate that you make money. Agree? So I have this one here. This is current, nominal. So I have this one here. I have this one here. I need to find this one here. So this one here is going to be, this one is going to be IC plus 1, or 1 plus this one, divided by 1 plus pi minus 1, correct? This is my real. Do you agree with me, guys?
Yeah.
Okay, so I simply apply my formula then. So this is going to be 1 plus 0.07 divided by 1.05. So this equals what?
6.47%.
So this is real. This is real. As soon as my investment profitability is larger than my cost of capital, correct? Then I do the project. Makes sense? These type of questions are very cool, guys. And now let's take a look to what is economic implication of all this stuff here. You have questions?
Just to make sure, it should be divided by 1.005, right? Because it was half.
Oh, yes, it is not 5%. It is. Yes, let me. Correct. Okay, questions, guys? It's clear? Okay, so now let's go and let's do some economic analysis here, guys. Do you remember what is the role of central banks? This is what is called, guys, a Taylor rule. So have you heard about the Taylor rule? Okay, so it's transparency and cleanliness and easiness of explanation of the rules, basically. Okay, but basically what these guys are, the central banks are focused always is in inflation, so low inflation. And basically low unemployment. They always mention these two goals as part of the mandates of central banks. Okay. No one talks about FX, guys. Foreign exchange, no one talks about them. However, take a look to what happens. So remember, we said that the interest in dollars, real, equals 1 plus devaluation, 1 plus the interest rate in Europe, divided by 1 plus pi minus 1. Agree? Now, can we just, what is the IDEF? Okay, so what I will do, this is going to be 1 plus I dollar real multiplied by 1 plus pi divided by 1 plus interest in euros minus 1. This is my devaluation rate. Do you agree? And I will write the same now in terms of pi. So this goes 1 plus pi goes up equals 1 plus I dep or $1 divided by 1 plus I dollars real. Agree? So pi at the end of the day
So on the top is euros, right? Correct. 1 plus I.
Oh,
What is?
yes. You're right. Give me 1 second. This one here. Oh, no. This is euros. So this is 1 plus, this one goes here, 1 plus dollars. Agree? This 1 plus pi multiplies. This is part here. And as soon as I just want I def, so that 1 pi plus I euros goes down, minus 1, and then we have I def. Do you agree with me?
Yes.
Okay. And the inflation in terms of all these components here hopefully is correct. Ready? One thing that is really crucial, guys, take a look. What is the relationship between, even though central banks say, oh, come on, I don't care about exchange rate. Of course, you must care about exchange rates. Because if your currency start devaluating, so what happens if this guy increases?
Sorry, that boxed equation should have a -1 at the end, right?
Oh, yeah. Completely right. Now take a look to what happens. Imagine, guys, that your currency starts depreciating. This goes up. So what happened with your equation? Inflation.
Inflation goes up.
Inflation goes up. Okay, so that's why, guys, central banks, you know, I don't know why they don't mention anything about that, but because I think it is because of the 70s and 80s, when the governments tried to control exchange rates, okay, and it was a complete disaster. So the governments don't want to say, you know what, I'm controlling my currencies. No, they use this word of floating, managed floating. So this implies, you know what, I just intervene in the market when I see that something really, really is going bad or volatility is too high. It's basically the open market operations that we were talking. When there is a lot of volatility, central banks normally intervene. Okay, why they intervene? Because they know that if they are an open economy, having a fluctuation affects their trade, but also can cause inflation, right? You remember that, we have discussed that already before, but now here that the transition mechanism is very clear. Okay. Make sense to you guys? Okay, so let's do another example, and then we go into more statistics now. Up to this point, guys, everything that we have said in the future is an expectation. Do you agree? So I believe that the exchange rate in 1 year is going to be this. I believe that the exchange rate in 2 years is going to be this, etc. Okay, so let's do one example that's going to help us to provide some insight on the things we're going to be doing, guys. So let's assume, okay, so let's assume that I have, so I am an investor in Europe. Okay, as usual. I want to invest in USA. Okay, so I have a loan of 1 million euros. The interest in euros, imagine, is 5%. I know that the project in USA produces, and let's assume 10%. Let's assume that the devaluation rate equals, let's say 8%, let's exaggerate, okay? Do you invest in USA? Okay, 5 minutes to do this. So in this case, I don't have inflation. I just want to do this simple. Ready, guys? Okay, 2 more minutes, okay? Okay, 1 more minute, then we start. Okay, so we do it or we don't do it? We do it. Okay, so let's do A first. Okay, so I need to see what is my cost of capital, first of all. So my cost of capital in dollars, as soon as I don't have inflation, is going to be all in current terms. So, okay, I don't need to do anything with this number then. This is going to be 1.08 that multiplies 1.05 minus 1, correct? So this is equal to what?
0.134.
0.134. So basically 13.4%, right? Okay, so I can compare this number with the internal rate of return with this number. Yes, because there is no inflation, so this is current, this is current. Then this is my cost. Remember, this is my cost. This is what really this 5% for a loan of $1 million, that's what it costs. So obviously, if the cost is larger than my internal rate of return, I simply don't invest. Clear? Okay. Now, what is my break-even devaluation rate? Okay, so let's take a look to my formula. 1 plus I divided by 1 plus I euros minus 1 should be equal to my I def, correct? Guys, yes? So what I've done is I simply move some of the formulas. So from here, the I def that makes a equilibrium point. So what is the equilibrium point? What is the meaning of the equilibrium point?
They won't earn, but they won't lose any money either.
Yes. So this implies that I want this to, well, it's much easier really without doing this, even this formula. Without doing this formula, it doesn't matter. So remember that perhaps, come on. It's much easier if we explain this way. So I know that this one here equals 1 plus I def 1 plus I euros minus 1. Do you agree? So equilibrium, guys, means that basically I want this part here to be equal to 10%. You agree? So I want this number here to be 0.1. So this is equal to I def 1 plus 0.05 minus 1. And then here's where the formula comes. Okay, so if you do the blah, 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 this is going to be 1.1 divided by 1.05 minus 1. Correct? This is my maximum depreciation rate. So this equals what?
I got 4.76%.
Perfect. 4.76%. So what is the meaning of this number? So if I def is smaller than this number, what happens? We do the investment or not?
You invest.
You do the investment.
Exactly. If the depreciation rate is larger than 4.76, you simply don't do it. And the third case is obviously if this number here equals 4.76, so you are indifferent. Oopsie, I cannot write. It's indifferent. Right? Make sense? Okay. And so once we know that that's why that the break-even, guys, is crucial and it's very, very important to learn. If we know this number here, we don't need to be making computations here. Correct? So what is the cost of, I will do only one. Okay, so what is the cost of capital here? This is going to be 1.02 that multiplies 1.05 minus 1, correct? So what is the cost here? What is this number equal to? Someone?
0.071.
0.071, like that? 7.1%. Right? So basically 7.1% compared with 10% is smaller, so I do the investment. Correct? But what is interesting, guys, is that once you understand the break-even concept, so from here you can immediately classify, oh, this one I do, this one I don't do, this one I don't do. You don't need to do anything else. Okay? So that's why this concept of critical value is crucial. Make sense, everyone? Yep. Questions? 1 minute to copy and then we continue. Yeah, questions? It's clear? Okay, guys, what I was telling to you is that indeed this number here, okay, this can be known at T0, right? Yeah, if I get a loan, I know this at T0. Unless this is a variable interest rate. So for example, it can be an interest rate plus LIBOR, okay? But in general, we know this at least more or less in great advantage. This one here, of course, this is always something that can change in time. But we are going to focus also on this one here. This one is an expectation. You see, it can be 8, can be 6, can be 4. You can have different models, different numbers. So what we need to do here, guys, is basically a sensitivity analysis. Okay, and for this sensitivity analysis, guys, we need to do a brief one class service, no survey, a summary of statistics. Okay, everyone is familiar with the statistics, right? Everyone. So good. So we have done a more in-depth analysis in econometrics. Makes sense. So let's do this. Let's start with this. Okay. Let me quickly move here. So good. So indeed, you are in econometrics. So we have done a very extended survey on econometrics and statistics. So you need to be here if you want to. Okay, because we're going to do a summary of the summary. So if you feel free to simply leave the class for today. I know that you are in 1 or 2 p.m. in the morning, or a.m. in the morning. Okay. So okay, guys. So let's start doing some statistics. So let's do a very quick review on the statistics that is going to help us understand all this stuff. Stats review. Well. And I will just focus on the things that are really important for me, guys. I need to arrive to confidence intervals, okay? Because that's the one that I need to do these simulations and stress testing. Now, the first thing we need to realize, guys, is we need to understand what is probabilities, okay? And for probabilities, what I will do is I will define the frequency table. Let's do first frequency tables. And let's do a very simple example. So imagine, guys, that the exchange rates during the last 10 months are the following, okay? So I will just write numbers. And let's say, okay. So this is FX monthly data. We have 10 observations. So N, my sample size, equals 10 months. And what I want to do, guys, is I want to create a frequency table. Okay, so I will create my frequency. So which one is the smallest value? 120. So perhaps we can do from 120 to 125, 125 to 130, 130 to 135, and 135 to 140. Okay, so these ones here are called class limits. So all of them are called classes. And these ones here, the upper and lower, are class limits. So these are classes and class limits. Okay, so the class limits are 135, 140. Now, the classes, guys, needs to be mutually exclusive. So basically, one observation cannot fall in 2 classes at the same time. And the classes must be exhaustive. Okay, so exhaustive means what? That all the observations here need to be in one of these classes. Got it? So that's why what I will do is I will use this notation. Do you understand what this notation means? This one not included. And this one included. So this means, for example, that 125 is included in the first class. 125 is not included in the second class. Make sense? And then what we do, guys, is simply count. How many of my observations fall in this class? How many in this, and this? Okay, can you help me with that? Then we have something that's called relative frequencies. Then we have cumulative frequencies. And then finally, relative cumulative frequencies. Relative. Okay, 1 minute to do the frequency, and then we do together all the other part. Ready? So you can tell me, between 120 and 125, how many do we have?
2,
2. To 125, 130.
6.
Oh, wow.
4. What? Hold on.
Oh, 4. Yes, 4.
4. Okay. 4. Okay. 130, 135.
3.
3.
And here?
1.
1. Okay. One way of checking, guys, that you are satisfying all, that you are including all the observations, remember, because we need to be exhaustive, is simply that the sum should be equal to the sample size. To the sample size. Agree? And now from here, how do we compute the relative frequency? We simply divide every single number by the total. So the first one is going to be 2 divided by 10, 0.2, 0.4, 0.3, 0.1. The sum must be equal to, of course, to 1. Correct? Now, how do we compute the cumulative frequency? We simply start summing the frequency. So the first one is 2. The second one is going to be 2 plus 4, 6. The next one is 6 plus 3, 9. 9 plus 1, 10. I'm simply accumulating. And then the relative cumulative frequencies, instead of accumulating the frequencies, I accumulate the relative frequencies. So this is going to be 0.2, 0.6, 0.3, 0.6, 0.9, and 1. And that's it. Make sense? Now, guys, something that is really important with probabilities. Let me finish with something else first. How do we graph these ones here? Okay, we have two ways of representing this one in a graphical way, guys. One is that the histogram. Okay, and for the histogram, what we do is we simply draw this one here. Here we go, here we put our class limits. Okay, so I start at 120, 125, 130, 135, 140. And then I simply say how many observations? 4 is the maximum. 1, 2, 3, 4. So we say between 120 and 125, I have 2 observations. Right? Between 125 and 130, we have 4 observations. Between 130 and 135, I have 3. And finally, I have 1 in this interval. So this is my histogram. Do you have questions, guys? There is another graph that is related to this one here. It's called the frequency distribution, guys. How the frequency distribution is graphed here, what we need to do is we need to find first something that are called class marks. What is a class mark? It's simply the middle point between class limits. So for example, here, one class mark will be simply 1.30 plus 1.25 divided by 2. It's the middle point. So here is going to be 1.275, correct? So this is my middle point. Here, my middle point is going to be 1.325. My middle point here, 1.375, correct? And then you simply project this into the top, of the rectangles. And then you simply join them with a line, okay? Here, here. And what do you do with the extremes? Because, sorry, this is Polygon of Frequencies. I'm tired, definitely. This one here is Polygon of Frequencies. This is what is called the Polygon of Frequencies. Okay, so please attention here, guys, because this is important. The Polygon of Frequencies always starts in the horizontal line. Right? But we don't have more observations below 1.20. We don't have observations above 140. However, what we need to do here is a guess. Okay, what we are going to create is we are going to create an artificial class that has the same dimension as a close to it. So I need to create here a 1.45, do you agree? And here we'll have a 1.15. These are artificial classes. Then you create the middle point of the class mark, this point here, and then you finish your Polygon of Frequencies like that. Make sense? These two, 1.45 and 1.15, are artificial classes. Class limits. Okay? Make sense? Okay, so let me do another one that is called OGIF. What is known as the OGIF? Okay, so the OGIF, guys, represents the cumulative frequencies, the relative cumulative frequencies. So again, I have my class limits. The maximum this number, the relative cumulative frequency, can take on is 1, correct? So we cannot have 1.5, no, by definition is 1. So I have my class limit. So remember, this is series around here, so it's not exactly the same. So I start with 120, 125, 130, 135, and 140. Got it? And what we are going to represent, guys, is the OGIF. Is a relative cumulative frequency. So here I have my relative cumulative frequencies. So I say between below 120, 0. Okay, so in my data, I have 0 below 120. Below 125, I have 0.2. Below 130, I have 0.6. You see here. Below 135, I have 0.9. And below 140, I have all observations, 1. Okay, so how my OGIF looks like at the end. So it starts from 0, goes up, goes up, goes up, and stays at 0. That's my OGIF. 1 minute to copy, guys. Okay, I need your full attention here, guys. Okay, so there are some properties of probabilities, guys. I will probabilities. So if I have, you know, first of all, let's do a definition. So probabilities are based on experiments. Okay, so an experiment is basically that, is something that you try to do. Okay, or you test, for example, what are the exchange rates during this period of time. This is my experiment. Experiment, guys, have something that's called a sample space. That is simply all possible results of an experiment. If I flip a coin, I have obviously only two possible results, head and tails. Okay, if I toss a die, I have 6 possible results, 1, 2, 3, 4, 5, or 6. Right? So this is the sample space. Then we have an event that is simple, a subset of sample space. Okay? And finally, I have probabilities, guys, that simply represent the chance of something happening. Okay? Now, probabilities have certain conditions. So imagine I call an event A, okay, that belongs to the sample space. So this, let's call this sample space gamma, omega. My event belongs to omega. So this implies that this has all the events. This one is simply a subset of the sample space. And I call this event A. So probability of A, guys, always is going to be between what and what?
Zero in the sample space.
0 and
The sample space. No,
no,
1.
no, 1, exactly. Then if you have one event and then you sum with all the probability of one event with the probability of its complement, is always going to be equal to 1. So this is all events not being A. So basically, all the other events that are not A. So take a look, guys, to the relative frequency distribution here. All of them are smaller than 1. All of them add up to 1. Agree with me? My experiment can be this one here. My experiment is simply looking around for monthly exchange rates. That's my experiment. What is my sample space? My 10 observations, 10 possible, well, my possible results. What can be one event? Well, whatever you can imagine. So one event is that my randomly, I select one exchange rate that is between 125 and 130, for example. Okay? So this one here looks like probabilities. You agree? Agree with me or not? But I'm using very carefully the word looks like. Why I'm not saying they can be taken as probabilities? What is missing here, guys? Why we cannot say that these numbers here can be used as probabilities? Do you understand what I'm telling to you, right? Why I cannot say that relative frequencies as they are here represent probabilities? Why?
It's a past event. I don't know.
No. Normally probabilities is developed based on past events. But the thing is the following, guys. Okay, let's do one just mentally. Okay, let's do one exercise. Do you remember this exercise of flipping a coin? What is the probability of having a head? I have a coin, I will flip it. What is the probability of I will get a head?
0.5.
0.5.
0.5, of course, 0.5. Okay, so this implies I flip my coin and gets tails. Well, okay, so this implies that next time that I flip the coin, I need to have a head, right? Because it's 50-50. Agree with me or not? No? Well, so why do you tell me it's 50%? You told me it's 50%.
It's 50% every time you flip it.
Okay. So that implies that technically if I flip once, flip again, I should have at least one head and one tail. Yes or no? No?
No.
No. Okay, I will do this 10 times. So this implies that it's 50-50. So I should have 5 heads, 5 tails. Yes or no? Otherwise, your probabilities really are terrible. But there is something missing there. Now, you can be very unlucky, guys, because we're looking heads. You can be very unlucky, and in 10 trials, you get 0 heads. Do you agree? So, but how do you, who was a crazy guy that said that was 50-50 then? In my experiment, if I don't get any heads, I can say the probability of heads is 0 because I never get one. So how do we get this 50-50% idea? What is the variable that needs to be modified? The 10, the number of trials. Now, guys, if you can do this exercise in Excel, if you move from 10 to 100 to 1,000 to 1 million trials, you're going to see that indeed you are going to be approaching the 50-50. Got it? And that's exactly what is missing to be sure, no, well, to be confident that these relative frequencies can represent probabilities. We can be really confident about these numbers representing probabilities if and only if the sample size is big. If the sample size is large, you know, I will write tens to the infinite. So it's a very large number. Then relative frequencies can be equivalent to probabilities. Okay, how do we call this one here? This here is called the law of large numbers, or LLN. Okay, and so that's the part that you need to understand here. If we have so imagine that these represent thousands of numbers, okay? So if you have 2,000 observations, 4,000 observations, 3,000 observations, so you're going to be more and more confident that this number here indeed represents probabilities. Make sense? And if we talk about 2 million, 4 million, 3 million, 1 million, okay, in that case, we're going to be almost sure that these numbers represent probabilities. Got it? Make sense to you? Okay, so the law of large numbers, guys, is going to be the one that is going to give us support that relative frequencies can be used as probabilities. Right? Okay, so now before moving, I will ask you some questions just to be sure that you understand this table here. So let me save, copy if you need to, 1 minute to copy, and then we can do some questions. I can write some questions for you. I will take a picture just to be able to write questions. Ready? Okay, so questions for you guys based on the tables that we have just written now. Okay, so based on the table that you have, okay. So one, I will assume that by the law of large numbers, the relative frequencies are probabilities, okay? So I'm assuming that my observations are not 10, are very, very large number. Got it? So please be careful there. I'm not talking about my 10, I'm talking about millions of observations, okay? So I can assume that my relative frequencies are probabilities. Got it? So my questions are going to be based on that. So what is the probability of exchange rates in 1.25 to 1.35? What is the probability of FX less than 1.3 inclusive? So including 1.3. What is the number of observations in 1.30? Oh, sorry, 1.30 is open to 1.40. What is the probability of FX larger than 1.3? Not included. Okay, 2 minutes to do this. One more minute. Ready? Okay, so you tell me. Let me move my picture. Here we go. Yeah, how many, what is the probability between 125 and 135? Someone?
0.7.
0.7? Guys, do you agree?
Yeah.
Perfect. Yes. So there are two ways of arriving to this number. It is this number plus this number, because I'm looking for 125 to 135, 0.7, 0.4 times, not times, plus 0.3, or the cumulative. Up to 1.35 is 0.9, correct? Up to 1.25 is 0.2. So between 0.35, 1.35 and 125, 0.9 minus 0.2. Got it? So there are two ways of finding the same stuff. You use the cumulative, you use the relative frequencies. Make sense to you? Okay, so this one can be equal to, this can be equal to the probability of being between 1.25, 130, plus the probability of 1.30 to 1.35, that is equal to 0.4 plus 0.3 equals 0.7, correct? Or the probability of being 135 is smaller than 1.35 minus the probability of being smaller than 1.25. So let me delete this clear. Agree with me, guys? So the probability of smaller than this is equal to 0.9 minus 0.2. You obtain your 0.7. Okay, good, easy. What is the probability of having less than 1.30, including 1.30? So basically, the probability of smaller than 1.3, including this one here, is going to be what? What, guys?
60%.
0.6.
Exactly, 0.6 or 60%. Now, number of observations. Now, when we talk about number of observations, guys, we talk about frequencies or of cumulative frequencies, okay, the numbers. So what do we get here between 1.3 and 1.4? 4, 1 plus 3, 4. Do you agree? And finally, what is the probability of fx larger than 1.30? So now I want probability of not including 130. Larger than 130.
0.4.
0.4.
Yeah.
Do you agree?
Yeah.
0.4. Now, guys, if I call this event A, okay, so what I'm talking is probability of A. How do I call this event here? Oh, well, I need to do one of them should be smaller or equal. Which one is included? This one is included, so this is like that. So how do we call this one here? If this is A, how do we call this one here?
Complement of A.
The complement of A. Because remember, if this is A, everything that is not A should be this number here. So basically, this is P of AC. Now, remember I told you guys that P of A plus P of the complement of A equals what? Always equals
1.
1. Okay, good questions. We're moving good, guys. We're moving good. So we're gonna be soon arriving to where we want to be. You remember all this stuff, right? Yep, all times. Okay, so let's go for something more. Now
It's
let's
like
go.
the GRE.
Sorry, yeah.
It's like the GRE.
That's it.
GRE flashbacks.
Right. Okay,
It's
so now, all
same
times.
stuff you learn in the GRE. Yeah.
Right.
Horrible times.
Okay, guys. So, oh yeah, let's define a random variable. So what is a random variable, guys? It's simply a variable that we know before the experiment all the possible results of it, all the possible values that a random variable can take on. But the final value, you're going to know the final value only after you finish the experiment. Okay? So, for example, if I have a die, I have 1, I have 1, 2, I have 1, 2, 3. My random variable is what? I can define my random variable x, okay, as number 2. Okay, sorry. My random variable x is all the possible results. So basically, my x is going to be 1, 2, 3, 4, 5, and 6. Do you agree? However, guys, do I know what is the final value of x before doing the experiment? I have no idea. Do you agree? I have really no idea. Which one is the final value? Well, finish the experiment. Okay. Once you finish the experiment, you're gonna for sure know which one is the result. Right? Now, there are two types of random variables, guys. One that is discrete. Okay, so very easy. Take an interval, and if between values you see holes, this is a discrete. For example, your age in years. Okay, and I want integers. So either you are 18, 19, 20, 21, 22. You cannot be 19.2, right? So if I define my age in years, integers, so this is a discrete random variable. Agree? Or obviously continuous random variables. You take an interval and all possible values of the interval of the random variable are feasible. For example, interest rates. 1.1 is possible, yes or not? Yeah. 1.111999 is possible? Yeah, it's possible. So any number that you can imagine in a given interval is possible, then we have a continuous random variable. Now, why these are crucial, guys? Discrete random variables create discrete probability distributions. And continuous random variables, of course, they create continuous probability distributions. Make sense? Okay, so let's go and define what is a probability distribution. Okay, so I define X is my random variable. I will continue with my example, guys. Well, it's going to be too big. Let me define X. My experiment is going to be flipping a coin once. Twice. Okay, so that's going to be my experiment. So what are my possible values? So flip a coin twice. This is my experiment. And I want my event, my random variable, number of heads. Okay. So of course, how many heads I can have? I can have 1, 2, or 0. Agree? So I can have head and tail. Or let's say head and head. Very lucky. I can have head and tail, tail and head, or I can have tail and tail. Correct, guys? So here I have number of heads. I will have 2, 1, 1, 0. I can attach to these ones here. What is the probability of each of them happening? What is the probability of having head and head?
0.25.
0.25. Do you agree with that? Because it is. The probability of having a head is what, guys? You told me 0.5, right? And the probability of having another head is also 0.5. So 0.5 times 0.5 is 0.25 because these are independent events. So probability here is 0.25, probability here is 0.25, probability here is 0.25, probability here is 0.25. Correct? Then what I will do is I can collapse these two because it's 1. So it doesn't matter. My example is not asking for heads and tails. It's simply asking number of heads. So what I will do is I will collapse. X is, remember, the number of heads. I can have 0, I can have 1, or I can have 2. What is the probability of 0? 0.25. What is the probability of having 1? 0.5. And what is the probability of having 2? 0.25. Make sense? Okay, guys. So this is a probability distribution. So what is a probability distribution, guys? It's simply the combination of two things. The random variable, my X, and my probabilities attached to each of the possible results, my P of X. This is what is called a probability distribution. So I have all the possible values of X, my random variable, and attached to each of these possible values, it's probabilities of occurrence.
So this would be a discrete probability distribution.
Exactly. This is a discrete probability distribution because I have discrete values. You see? Remember, if I do my interval between 0 and 2, I have holes between 0 and 1. I have holes between 1 and 2. Okay, perfect. Now, of course, here what I can do is I can graph this one using the histogram. So if I want to do the histogram, I do, well, I will write 0 around here. Well, 0, 1, or 2. So I have between 0 and 1, 0.25, 0.5. I have this one. In 1, I have this one. And in 2, I have this one here. Okay? Make sense? So I have my histogram here. Now, guys, something that is crucial is to learn 2 moments. Remember, guys, that always when we talk about the statistics, we always have central tendency. So more or less where the values are located the most. And we have dispersion, how dispersed the data is, right? And we use 2 measures. We use the expected value. When we talk about probabilities, guys, we call it about something that is called expected value. That is simply call it the mean, right? Or the average. So, but indeed, what is my expected value is simply going to be defined by I equal 1 to n of xi, p of xi. So let me write first the formulas, and then we do this together. And then we have the variance of x, that is simply sum of I equal 1 to n of xi minus, I will call this one here, guys, x bar, okay? So the mean, x bar minus x bar, just to make it easier, square times p of xi. So these two formulas are going to be extremely useful for understanding what we're doing, guys.
Sorry, Professor. Can you go back again to the two equations you put?
Yes, I will solve them. Huh? What I'm telling to you in this formula, Daniel, is very simple. So this implies multiply, this is x, this is xi, x1, x2, x3, right? This is p of x1, p of x2, p of x3. So in our example, the expected value of x, how many observations do we have? From I equal 1 to 3, right? Of xi, p of xi. So this implies that what I need to do is the following. I need to multiply first element by element, x1, p of x1, plus x2 times p of x2, plus x3 times p of x3. P of x3. Okay, so this implies, what is x1? Position. Is x position 1 is 0, right? So it's going to be 0. What is the probability of 0? 0.25. What is the value of 2? X position 2 is 1. What is the probability of 1? 0.5. Plus, what is the value of position x, position 3 of x? 2. The value of the probability is 0.25. So if you do this, this is 1. No, sorry, this is 0.5, this is 0.5. This is equal to 1. So in average, guys, what is the expected value of your experiment? 1. So basically, in average, what I expect is to have 1 head. Right? So that's the meaning of this one here. The dispersion is more, how dispersed the data is. Okay, the larger the dispersion, the more risky the profile becomes. Now, can you please compute the variance? Use this formula.
Professor, just quick question.
Yep.
Is the expected value normally the one that has the highest probability, or not necessarily? Because, like, it's just 1 because the probability is 0.5. Or
no,
it just so happens that
not
that's what came out.
not necessarily true, but most likely yes. Okay, we're going to see examples in which not necessarily this is happening, because the problem with expected value is that the expected value can be moved to the right or to the left given outliers. Got it? So not necessarily you're going to have the highest probability. The one that has the highest probability always is the mode. Okay, the mode is the element that repeats the most, remember? Okay, yeah. So the mode, yes, it will have for sure the highest probability. However, the mean, if you have a symmetric distribution, yes, the mean is the one that has the highest probability. Got it? If the distribution is not symmetric, this doesn't hold anymore. Okay, can you please compute the standard deviation, guys? Ready, guys? So we do the same formula. So this simply is sum of I equal 1 to 3 of xi minus x bar. So by the way, this is x bar, right? Just simplification. Square p of xi. So this implies the first one is going to be x1 minus x bar square times p of x1 plus x2 minus x bar square p of x2 plus x3 minus x bar square p of x3, correct? We simply replace the values. This is going to be 0 minus 1 square times 0.25 plus 1 minus 1 square times 0.5 plus 2 minus 1 square times 0.25, correct? What do you get here, guys?
0.5.
0.5. And what is the problem with the variance, guys? What are the units of the variance? If we're talking about dollars, what are the units of the variance, guys? If we're talking about dollars, it's dollars square. Do you agree? Because we're squaring a number. So that's why we don't use normally the variance. What we use is something that is called the standard deviation. So this one here, let me call it, is called variance. This is called expected value. So remember, guys, that expected value is simply a weighted mean. Do you agree? The weights are the probabilities. Okay, so instead of using the variance, what we use is something that is called a standard deviation. That is simply the positive of the square root of sigma square. Because remember, the square root can be positive or negative. Okay, so in my case, it's a square root of 0.5. This is equal to what? Someone can take the square root of
Like 7.1.
0.71. And that's it. Okay, so the dispersion doesn't, it tells you that how dispersed is, but better if we compare with something. We are going to do this in the next class. Okay, I think we stop here, guys. Next class we finish with this, and then we are going to put the idea here is the following, guys. I cannot trust a single number. So if I'm doing a project, international project is more important here. I need to forecast what is going to be the exchange rate or what is going to be the devaluation rate. Got it? So I cannot trust in a single number. So if I do a forecast, so I believe it's going to be the IDEF is going to be 0.5. I cannot trust that number. You know, I need to create a confidence interval. You know what? It will be the depreciation rate for next period is going to be between 2% and 3.5%, for example. Right? And that number is crucial because you have now up to this point we have break even, so we understand what is a break even. But then if we have the confidence interval, I can create a lot of scenarios. I can say, you know what, worst case scenario, I will be at 95% confidence level. I will lose this money. But I can make this money. You see? So in that case, basically what you are trying to understand is the risk profile of your investment. And that's what we're trying to do at this point. Got it? Make sense to you? Okay, questions, guys. I need more time to do that next step, that is probability, like normal in the T. Do you have questions? Otherwise, we stop here. No? Okay, guys. So we see you next week. Anything that you need, you just let me know. Write me an email or, you know, whatever. We can get in touch. Okay, guys. So take care. And
Thanks.
see you. My pleasure, guys.
Professor.
Take care. See you later, guys. Take care.
Thank you.
Bye.